All right, so welcome to lecture 21. This is going to be on MOS, small signal model, and common emitter amplifiers. We'll start the common emitter amplifiers. I guess the first thing, though, is how many people actually watched the lecture from last time? Meaning the one that was recorded Wednesday? Yeah, everyone did? Okay. And this is the majority of the class here, of course. You'd be happy to know that your exams are all graded, and we actually can give them back to you today. But because, you know, unless more people don't show up, unless people show up, we won't do that until next. No, we'll give them today. But we won't do it till towards the end of class to make sure everyone who shows up. So just a couple other announcements. One, homework number 7 is online, and that's going to be due next Friday via Gradescope. Lab number 5 is already online as well, and I'm going to talk a little bit about lab number 5 right now, because this actually is your first project. This is actually a 3-week lab, and so it's not going to be due till November 12th, and so it's not going to be due for a while from now, but it's a design project, and so you actually don't have all the material that you need to do this lab yet. But you're getting it now anyway, so you can take a good look at it. And I already said this. So why don't we start with the lab, and let me bring that up here. Okay. That's the solutions to the midterm. Here's the lab. Okay, so the lab, this is your lab. This is going to be the design of a common emitter amplifier. And you've sort of seen, if you watched the last few lectures, you're sort of seeing how this is coming together. You're going to design this amplifier. And so for this time, we're actually going to give you the structure of the amplifier, the complete topology of the amplifier. So you got a bipolar transistor here. You got some capacitors we're going to talk about that are intrinsic to the bipolar transistor. You have this resistor network that you already kind of know about because you've done your lab and you've seen the lectures from last time. This is for biasing. You got parasitic capacitors, you've got coupling capacitors going in and out of this that we'll talk about today, a source resistance, a load resistance, etc. And so what you're going to need to do is design these resistors and this transistor here so that, and these capacitors around it, so that you get a very specific spec. And so this amplifier is going to give you a certain amount of gain that you need to have. In this case, we want 270 volt per volts of gain. You're going to have a lower corner frequency of 100 hertz. You're going to have an upper corner frequency of 85 kilohertz. Your rise time has got to be less than 5 microseconds. Your undistorted output voltage swing, which we'll talk about in succeeding lectures, has got to be greater than 1.5 volts, 0 to peak. This is on a 12 volt rail, so you're going 12 volts to ground in this. You have to meet the specifications while loaded by an oscilloscope probe, which is this 10 megaohms here, but also, and the oscilloscope probe will also have some capacitance associated with it, but you're also going to stick in 39 picofarads of capacitance in the output load. You want to minimize the total external capacitance, so this capacitor CE and this capacitor CC1, you want to make as small as possible to still make this work. You want reasonable bias stability. In past lectures, you've learned about what you need to do for bias stability. This is just that equation that was just in the lecture right now. So the RE here needs to be something relative to the RB, which is created by the R1 and R2. All resistors and capacitors must be the standard values in lab. I guess I'm saying 10% here, but what are the lab values? Are they 5% or 10% resistors? They're 5? Yeah, so then 5%. These things, circuit topology, and using a 2N3904 transistor, which you have in the lab. And so the lab has got 3 phases. So the first, you got to start with a hand design, then you got to do a SPICE simulation, then you actually have to hook this up onto your breadboards and test this to make sure that it works. And, you know, you're going to write up a lab report describing this. This report now is going to be different than the reports you've been writing. It's not just going to be the answers to the questions, but you need to actually write something up that describes more professionally what is going on with this. And so this gives you some inkling of what your lab report should have. Now, so I should say you're still working in pairs, but you each need to turn in your own individual lab report. And in this case, you're right, if you're doing your own lab report, they should not look the same as your partners. I mean, there should be differences. Certainly some of the numbers might be the same, but when you're writing up things for discussion and that sort of thing, they should look different. We're not looking for excessive paperwork, so basically we want no more than 10 pages of text and figures. And so this could be something that's typeset. For derivations, you can use hand-derived things if you want. You know, you can piece the whole thing together, but it should look nice. You should have sections on each of these areas, and this is giving you sort of the percent that they're worth when you turn in that report. This is kind of open-ended here. This is sort of seeing how well can you write a report, how well can you describe what you've designed. And so there's a design strategy and discussion. There's your talk about your hand design. What equations did you use? How did you use those equations to sort of guide you in how to change certain parameters in order to meet the spec? SPICE simulations, experimental results, and some summary table like you find in professional journal articles, actually, where they will summarize the specs they were looking for, the specs they actually got, and maybe comparisons with other work, which you won't be able to do because there is no other work on this. But a nice table there. And so on and so forth. You can read the rest of this here on what's going to be needed in the report. But the main thing is that this is starting, I suppose, next week. And so you're getting this right now. I don't know how much of this you can do immediately next week. Probably not a lot. But this will be your Lab 5. It's your first project. It's worth a lot of points. And so it's something to pay attention to. Okay? Any questions about this and the logistics around this? Okay, this is online in the lab link on the website. Okay? All right. We'll talk a lot more about this as you start getting the material to actually do this. Again, you don't have the material yet to do this. I have the solutions for the exam on this too, and I'll pass that around. But I'll wait a little bit just in case someone wants to wander in. Okay. So from there, let me go ahead and start the lecture. I guess before that, any questions about logistics? I know it was a tough Wednesday for you. You had a midterm, then some of you had to go to lab. I guess it's a tough day today too, because there was a homework due at 12. Now there's a lab due at 8. Yeah, everyone done with the lab? Okay. Hopefully that's not too much for you, but we're kind of caught up. And I don't know if you saw the emails from campus, right, saying that we can catch up in the RRR week. But maybe we don't have to do that because I recorded the lecture, I put that up online and that sort of thing. So I'm hoping we don't have to do that. But if we do, we'll do it, right? And you will enjoy it, I'm sure. All right, so lecture topics today. We'll talk about the T model. That's kind of the last thing that I touched upon in the last lecture. And then we'll start taking a look at PNP transistor models. So the hybrid pi model, which is a small signal model for a PNP transistor. And then we'll look at a saturated NMOS hybrid pi model. And then finally, we'll look at an example of small signal analysis where I'll sort of do a common emitter example on how to do the complete small signal analysis of an amplifier. And that's going to take a couple of lectures. We're definitely not going to finish that in today's lecture. So just to start here, we derived this last time. We derived this model for a transistor. So this is the base terminal, that's the emitter terminal, that's the collector terminal for an NPN bipolar junction transistor. And before we talked about large signal models for that, so DC large signal models. This is a small signal model for the transistor. And that's one of the things that people get confused about when we talk about large signal and small signal. This is just for small signal here. And I think I'll make that very clear when I do the example small signal analysis. But right now, this is only when you have a small signal coming into the base. You may have a larger signal on the collector, but we're using small signal because, again, the transistor is a nonlinear device. And so we can only put tiny signals into the base. And we'll talk about why it's okay to have large signals going across the collector. That has to do with the transistor characteristic, which you kind of already know. It looks very linear after the transistor is in forward active for a bipolar transistor and after it's saturated for an MOS transistor. But right now this is the model. And so anytime you want to do a small signal analysis, you can just replace the transistor with this model and then do just regular KCL, KVL type circuit analysis to solve that circuit. That's the way you'll do it initially, but before we're done, hopefully you don't even have to think about this model. Okay, I'm showing you this model right now to tell you where it comes from, and you'll be working with it. It'll be important to know this model, but hopefully by the end of class you won't even think of this. You'll just see the transistor symbol, and you'll be able to analyze without even thinking about this model. Okay, but that's a long ways from now, so I'll mention that now, but we're not doing that definitely today. And so just some remarks. I did this last time as well. So with this model, you can look at this and you can see that it sort of models the resistance going into the base. It's kind of like that R pi, but it's not really that R pi. It's a little more than that R pi in some situations when you have a resistor on the emitter, and we'll show some of those circuits later on. But you see a resistor at the base, you see a resistor on the collector. You might ask, where is the resistor going up the emitter? Okay, well, the resistor going up the emitter is represented in this by all of these elements right here. Okay, so we don't have to explicitly show a resistor at the emitter. All of these model that. And so we sort of did this last time, but if you want to think of the resistance seen looking up into the emitter here, how do you get that? You sort of say, well, if I got a voltage VBE across this, that's the resistance. So I put a test voltage down here, and I would have a voltage, it would drop a voltage VBE across this, which would then source a current. I guess when you put the test voltage, usually the voltage would be plus to minus there, and the current direction will be going up into this. But in this case, it's also the same thing as the voltage direction being this way and the current going down, right? And so in that respect, I could say that the resistance seen looking up this way is going to be equal to this voltage VBE divided by this current I sub E, right? Where these are now small signal voltage and small signal current. If I go ahead and do that, I can use some of the derivations we already have. So I know VBE is the voltage that I might drive this with. I know that this current here is I sub E, but I also know from the previous discussion that I sub E is just equal to the collector current I sub C divided by alpha. Remember, where alpha is equal to what? Who knows what alpha is equal to? Yeah, it's beta over beta plus 1, but what's the number? Yeah, it's about 1, isn't it? Right? So it could be 0.99 or something like that, but it's pretty much 1. Okay, so I can rearrange this some more, put the alpha on top, move the VBE, IC, VBE down here. That would be IC over VBE, but IC over VBE is just GM. Right? And I know what GM is. That's IC over VT. So if I plug that in, that's the DC IC divided by the thermal voltage VT, which is 25 millivolts or 26 millivolts, depending on who you talk to or what temperature you're at. But this then becomes IC over alpha, which is just capital I, capital E. So this RE resistance, this small signal resistance seen looking up into the emitter, is just VT divided by IE. Okay? And so the question is, why is that not represented here? Well, it's because if you did the analysis on this hybrid pi model right here, if I went and put a test voltage here and found that test current going up in that direction, that should give me RE when I divide Vx divided by Ix here. And last time we did this, trying to get the other side to move. Not sure why it won't. Okay. So last time we did this, here's that math there about that, whoops. Here it is. Right, so here's the math there. If we're using a test voltage source Vx and Ix going up, we did this last time and we found that looking up into the hybrid pi model, we do indeed see RE, little RE. So the whole model is consistent on all terminals. We see the right resistance looking into any of those terminals, so that gives us some confidence that everything is fine. You might still ask the question, well, why not explicitly put in RE? Well, you can explicitly put in RE. You just have to go to a different model, the common base model. So the common base model, which is often called the T model, because it looks like a T, at least a sideways T. Okay? And so this common base T model here, you do have the RE resistance explicitly there. You don't show the R pi resistance. See, there's no R pi in any of these here. but you explicitly include the little RE, and instead of a voltage controlled current source up here, you now use a current controlled current source where this IE current controls that collector current, and you know that they're related to one another by alpha, and so that's why that's alpha times IE. You can also, if you want, express this current source as GM times VBE. That's that same current source. Okay? And then the R naught in this, if I really wanted to be very complete about this, there is an R naught in this circuit, and it's right here. I'm just ignoring the R naught now, which we'll do many times later on. But there's actually an R naught right there. And I can put that here as well. Okay, so that ends up being the T model. It is completely interchangeable with the hybrid pi model that we've been talking about. Okay, so just remember that. There are some circuits where the hybrid pi model makes them easier to analyze. There are some circuits where the T model makes them easier to analyze. And if you know the T model, you are in an advantage, because there's a good number of important circuits where the T model is just easier to analyze. You can always get it using the hybrid pi model, whatever you do. But the T model will make it a lot easier for you, okay, in some circuits. Okay, so that's small signal models for NPN transistors. We spent a good amount of time on that last time. That's why I'm not going to spend even more time right now. But I will now talk about small signal models for forward active PNP transistors. And so a lot of our effort, in most courses, we spend a lot of effort talking about PNP transistors. NPN transistors, but PNP, you know, usually I just leave that up to you to figure out. Luckily, that's very easy to do in the small signal world, because in the small signal world for PNP transistor, yeah, the symbol looks a bit different. Instead of the arrow being at the bottom here, the arrow's up at the top. But I can really just treat this as an upside down hybrid pi model for NPN. So if I go in and I still say that's the emitter, that's the base, that's the collector. I put the base and the collector at the bottom and the emitter at the top here. That current source will still go from the collector to the emitter as long as I'm still using VBE in this direction, from the base to the emitter there, when I represent my voltage controlled current source, and this then becomes GM times VBE here. The R naught stays there. You can see all the directions for the currents are the same as in the NPN case. And so let me go back to the NPN. Now, I guess I don't show the current directions there. But you see, this thing is just that flipped over. All right? And so if you can remember that everything stays the same, then hopefully that makes it a lot easier for you to at least do small signal NPN and PNP in these analog circuits. Okay, now you can, if you want, make the currents go in the other direction. So you might want to think of the currents going downwards, because usually for a PNP transistor, usually for any circuit we draw, like I've said in previous lectures, the top is going to be the higher voltage. The bottom will be the lower voltage. So currents will always want to flow down the way that we draw these things. Okay, so if I'm doing this, it looks like the currents are going up, okay, which they can if they're small signal currents. Right, so the large signal currents will want to go down. The small signal currents can go up and down, either way. Okay? And if you don't quite understand that, I'll show some pictures that will show you that that definitely is the case. But if you wanted to think of the small signal currents going down too, then you can reverse the polarities of these currents. But at the same time, you'll want to reverse the polarity of this EB and that arrow there and draw it like this. So these are two equivalent circuits here if you want to think of a small signal analysis for PNP. Okay? So let's see if I do anything else for PNP here. And you also can get a T model for PNP as well. And so this is the same as that NPN T model, except I just flipped it upside down. Okay? And I guess I could show the end. There's the NPN T model right here. You can see this is exactly the same thing, but I flipped it upside down. And all the directions and voltages are still going exactly the same way as they were in the NPN. Okay? That's just for small signal. They're the same. Okay, hopefully you can remember that, and anytime you see a PNP transistor, it doesn't bother you. You can just treat it just like the NPN case. If you need proof of all of this, then I have a little proof right here that I'm not going to spend a lot of time on. You can read this by yourself. It's the same proof that we did for the NPN case, except in this case, You know, when I look at the PNP model, right, in this model here, I guess we'll spend a little time. Remember, little I, capital E means that's the total current. Okay, and little I, capital C means that's the total current. Same with little I, capital B. And then the small signal currents are these. Small signal currents can go up, but all the total currents need to go down because the voltage is higher at the top than the bottom. Okay, but in this, right, I could take I sub C, and if that's I sub C, and if this is my direction for little I sub C in this case, then the total I sub C is going to be equal to the DC I sub C minus that I sub C. Okay, and the total of VEB in this case, up here, is going to be the DC VEB minus the little VBE, which is the small signal VBE. So those minus signs then come in, and because of them, you can go through this analysis, you end up with exactly the same equation for GM, which is capital I, capital C divided by VT, okay, which is the same equation as for NPN. All right, I'm going a little fast on this right now because I really want to get to NMOS transistors. I sort of did all of this in the last lecture, but now we've reached that point. We've reached NMOS transistors. So let me slow down a bit. And let me derive the small signal circuit for an NMOS transistor. This is the circuit you will replace the NMOS transistor with when you're doing a small signal analysis. Okay, so this is the small signal model for saturated NMOS transistors. And so I should mention that everything that I've done for the bipolar transistor, you notice, has been forward active. Okay, so like I said before, for analog circuits, forward active is where you're always operating the bipolar transistors. For NMOS transistors, for analog circuits, generally always you're operating them in saturation, okay, or in linear, like you saw in your previous lab number 3, I think it was. Right? Yeah. And so this is for analog. I should say right here, right off the bat, this is for analog applications. When we do digital applications in the end, you're going to see that we operate those transistors in all regions. They'll go from saturation to linear to cutoff as they transition from a 0 to a 1 or a 1 to a 0. Okay? But for right now, we're looking at our MOS transistor, so I'm going to draw an MOS transistor here. We're now looking at this transistor. And for this, of course, I'm going to have a gate, a drain, a source. I'm going to have the small signal voltages that I'll put across are little VGS. Little v, little VG, little GS, right? I'm going to have a current flowing down here that's going to be little ID, and I'm going to have a voltage across this, which I'm going to call little VDS, right? So same voltages as a large signal case, except I'm just making small signal versions of them, so all lowercase variable and subscript, okay? And so what I want out of this is the small signal equivalent circuit. And it turns out that small signal equivalent circuit is going to look a lot like the bipolar version of that circuit. After all, it is still a transistor. So I'm going to have my gate over here. That's going to feed into now, you know, what's separating the gate from the channel in an MOS transistor? It's a capacitor, right? I'm not going to draw the capacitor in right now. I will later on, but right now, let's just do all of this at a lower frequency, I suppose. So I won't include that capacitor now, but it's going to be just like the bipolar one in that I'm going to get a current source here. That's a voltage-controlled current source that's now being controlled by the voltage between the gate and the channel, which really is the gate and the source is what we usually reference that to. And so my source is going to be right here. And then I'm going to also have a resistance connecting my drain and my source. So the drain is going to be right here. And this I'm going to call R0, just like I called for the bipolar case. Okay. Now there's one more thing in this that I'm not going to draw just yet. But, you know, this is the basic circuit that you'll use most of the time. Okay. And so we're going to do the same thing that we did to derive these small signal elements. I want to know what GM is. I want to know what R0 is in this. And once I can get GM and R0, I have specified at least the small signal behavior of this transistor. And so let's go ahead and get these. So let me just say where here. GM is going to be a conductance again. So it's the conductance where I'm going to take my small signal ID divided by my VGS. Okay, so that's going to be equal to the derivative of my total ID, which I'm writing as little I, big D, with respect to my total gate to source voltage, but evaluated at my operating point, which I've been calling my Q point. The Q stands for quiescent point, so often people will use that for the DC bias point. And so we can do this because we know the equation for I sub D, little I, big D, for a MOS transistor. And so this is just going to end up being the derivative with respect to VGS, V capital GS, of 1/2 times mu n times Cox times W over L times VGS minus the threshold voltage VTN squared. Okay, and all of that evaluated at the Q point. Okay, if I go ahead and do this derivative here, I see my VGS in there. The 2 is actually going to come down and cancel that 1/2, so I'm going to end up with mu n times Cox times W over L times VGS minus VTN. Evaluated now at the operating point, VGS is equal to whatever the large signal gate to source voltage is in this structure. So in this case, the total voltage across here is going to be V capital GS, which is going to be equal to capital V capital GS plus that little VGS. Okay? And so therefore, this is one expression for GM here. Therefore, I could say that the expression for GM is going to be mu n times that Cox times W over L times that capital V capital GS minus the VTN threshold voltage. That's one expression for my GM for an MOS transistor. So it's not as simple as the bipolar. The bipolar, remember, is just the collector current divided by the thermal voltage VT. This is a little more complicated, but not that much more complicated here. And I can even put this in another form here if I remember that, again, my ID is 1/2 mu n Cox times W over L times VGS minus VTN. So this is the DC ID. If I remember, this is my DC ID. And I should also say that when I'm writing Cox now, I'm being a bit lazy, because before I wrote it as Cox double prime. This is still Cox double prime. Let me just say that here. I'm just being lazy and not putting the double primes on. Okay, I'm being lazy on purpose because all the books do this. Okay, I did the double prime in deriving this so that you understand that it was a capacitance per unit area. But in books, when they show a Cox, it should be understood that's a capacitance per unit area. They don't put the double prime there in books and in journal publications and that sort. So I'm going to start doing that there, right? But this is still the same as Cox double prime. I'm just being lazy, not putting the double prime like everyone else is. Okay. Okay, go back to this. And so in the end, if I plug this into this, this ends up being another form for GM, which is 2 times mu n times that Cox times W over L times that drain current I sub D. Okay, so those are the two forms that we have for little gm in this case. And so let me put a little box around this. That is a small signal GM for an MOS transistor. And so when you're doing small signal analysis, you're going to be using that equation quite often. It'll be a very important equation for you. There's one thing I do want to point out with that equation as well, because a lot of people use this language here. But this voltage, VGS minus VTN, you see all the time, the gate voltage minus the threshold voltage. That is given a name here. And so I can actually use this to back calculate what that is. From this ID equation, I can back calculate VGS minus VTN. And if I do that, I end up with VGS minus VTN is going to be equal to 2 times ID divided by mu n Cox times W over L, and that whole thing under a square root. That is often called VOV, which is the overdrive voltage. Okay, which makes sense because that's how much voltage you have beyond the threshold voltage to turn the device on, right? When you reach the threshold voltage, you've turned it on, but now you've gone beyond that, and the number of volts you've gone beyond that is this overdrive voltage. Okay? And so oftentimes I can just replace this VGS minus VTN here with just V overdrive, VOV, and that makes the GM equation look even simpler there. Okay, so I've got GM. Now all I need to do is get R naught here. And so how do I get R naught? Same thing as for the bipolar case, except now I'm using MOS variables. So I need VDS, the voltage across this. I guess I got to make that look like an ID. Okay, VDS divided by ID is going to be that R naught. Well, I don't have an equation for VDS in terms of ID, but I do have ID in terms of VDS. So I'm just going to write this as the inverse of the reciprocal, of the derivative of the ID equation versus VDS. These are large signal quantities here, evaluated at the operating point. And I said the reciprocal, so I'll take the -1 of that. Take that to the -1 power. And so in the end, this ends up being the derivative with respect to VDS of, and I guess just put that bracket for the -1 at the other side, of the equation that I know. It's still that saturation equation, 1/2 mu n Cox times W over L times VGS. This should be the large signal VGS. So little v, capital GS, minus my threshold voltage squared. But remember, I have this channel length modulation going on. So this is then going to be 1 plus lambda times the large signal VDS here. And all that I'm going to evaluate at the operating point. So that's Q point here. And that whole thing is to the -1 power. And you can see none of this stuff depends on VDS. The only thing that depends on VDS is out here. So it's a very simple derivative to take. This ends up just being equal to ID times lambda. That whole thing evaluated at ID equals capital I, capital D, which is the operating point, which ends up then being equal to lambda times capital I, capital D, to the -1 power, which says finally that the R naught that I'm looking for is just equal to 1 over lambda times ID. And that's your equation now for R naught. You'll be given lambda, right? It's usually going to be around 0.01 to 0.05 for the types of transistors we're looking at. But that's it then. That is the small signal equivalent circuit for an MOS transistor. And so we did that for bipolar. You can see this is the same technique that we're using for this device. And so, for example, in the second midterm or in the final, if I threw some device at you that you've never seen before, and I asked you for a small signal circuit, you should be able to derive all this for me. Right? That's where you have to take derivatives and that sort of thing. If I asked you to do that on a midterm, would that be mean? Maybe not that mean, right? Because this is one of the fundamental things you should be learning in this class. But at least you know how to do it. You've seen it done twice now with bipolar and with MOS here. Okay, and so one more thing though, so that I should say that's not the complete model. So MOS throws another crink into the model here that makes it a little more difficult than bipolar in some instances for small signal. And so what we'll find is bipolar is very easy small signal wise. Bipolar is very easy DC wise, DC bias wise, but it's a little more difficult small signal wise. MOS is very easy small signal wise. It's more difficult getting a DC bias for MOS. So you'll see that as we do more lectures here. But what adds to some of the complexity of MOS, which is already more complex even without this addition, is that if I have, in MOS, those aren't the only terminals. I also have a bulk terminal, right, in MOS. And so I can actually have a voltage between the bulk terminal and my source, VBS. And so I'm writing that as a large signal bulk signal here, but this actually is equal to, right, the DC term plus the small signal VBS. And this, right, what is this doing? When I change VBS, what does that do to an MOS transistor? It changes the threshold voltage, right. And so if my threshold voltage changes, but my gate to source voltage doesn't, that's still going to cause a change in my current ICD. Okay? Which means I have to model that now with my small signal circuit. So I'm going to go ahead and do that. So I'm going to add one more voltage controlled current source here, just like the one over here, except this one now is controlled by the body effect. And so I'm going to call that GMB, and that's going to be controlled by this small signal voltage, little VBS. Okay, this is an often neglected thing. But for short channel devices, this becomes more important to include in the model. Okay, so in modern times, we're seeing this modeled more often. And so how do you go about getting this? Again, it's a threshold voltage effect. So our threshold voltage, V sub t, is going to be equal to some function of the large signal VBS as you've seen before, right? And so this gives rise, slow down, to what's called a body effect transconductance. Which is a little more involved to derive, so I'm actually not going to derive it for you. I'm just going to show you the formulation needed to derive it. You basically have to take that ID equation, take the derivative with respect to the bulk to source voltage, which means you're going to have to replace in this VTN as a function of bulk to source voltage. And as usual, evaluate that at the operating point. If you went and did that, you would get GM times a gamma factor, which you've seen before with the body effect, right? That's the body effect parameter, divided by 2 times phi f plus VSB, capital V, capital SB. This then is equal to the GMB that you see in this model to the left there. Okay, so now we've completely modeled the MOS transistor, at least for lower frequency type applications. And so now that we have all these models, right, we've gone through modeling these devices, and we spent a lot of time doing that. When are we finally going to actually use them in circuits? Well, that's what we're going to do now. Okay, so with all these models, let's move on now to talk about how to analyze an amplifier. And that's where we talk about small signal analysis. Okay. So this is the procedure now for small signal analysis. We're going to practice this on what's called a common emitter circuit. And so this common emitter circuit takes a bipolar transistor Q1. It hooks it up just like that lab that I showed you, right? Lab number 5 is basically this, with a few different crinks in it there. But if you look at this thing right here, what we're doing is we have an input on this side here. So this is actually our source. So let me specify this here, all of this stuff here before that capacitor, like that. This is the source, or our input to this amplifier. And you notice what this is. It's the voltage together with a resistor. So this is a Thevenin equivalent that I'm drawing here. Okay, that's my source. This part right here, all the way up to this point, this is my amplifier. So my bipolar transistor is doing amplification, and it's exactly what you think amplification should be doing. I may put a very small signal here. By the time I get to the output, it's going to be a much larger signal. So what's happening is this source consists of a DC component, this V sub S there, and an AC component V sub S there. And so this really looks like this. That's time, and this is that V sub S. I have the line down it to say that's a capital S. Okay, so it looks like a money sign, but it means I'm trying to make a capital S. And so I have a DC level. That level there is this capital V, capital sub S. And then on top of that, I have this small signal component, where the small signal component is that little V sub S. Okay? So that's what I'm talking about. The total signal is the DC component plus that small signal component. Okay? And at the output, what I expect to see is something similar, except that this will be my output voltage. Well, I'll put a line down that to show that that's a capital O as well. So this will be at some other voltage here, V capital O. That doesn't have to be the same as this V capital S here. But I expect now this sinusoid to be much bigger. Okay? And so this is now going to be little v, little o. And that's no longer a small signal, but I'll tell you why we can get away with that at the output later on. But this is basically what we're doing. Right? We're treating this as something that can take a small signal and gain it up to a larger signal. Same thing that a speaker will do when you speak into your microphone. It goes to an amplifier, and then your voice becomes a lot louder. Okay? Or your cell phone picking up very weak electromagnetic signals, and then it's amplified up to a signal large enough that it can actually process it, turn it into voice, or turn it into data that you're trying to see on your cell phone. And so this final thing, this RL out here, this is the load. So that I'll just call our output load. And in this case, I'm assuming that's resistive. You'll notice that I'm connecting my input source to the amplifier with a capacitor. Capacitor is 10 microfarads, and a capacitor at the output also 10 microfarads. What's happening here is that if the frequency of the input signal is large enough, this capacitance becomes a short. And this capacitance becomes a short. Okay, all these capacitors are really doing is allowing you to have a different DC voltage here than here. Okay? And here than here. Okay, we'll talk about that more once we go into the small signal analysis. Okay, so that's identifying parts of this amplifier. And so here's a specific problem we're going to try to solve. For Q, which is this transistor, Q1 there, say it has beta equals to 100. Say it has an early voltage of 100 volts. Okay, find the voltage gain, V out divided by Vs. Okay, and then draw the collector voltage waveform for Vs equal to 0.014 times the cosine of omega naught t plus 1 volt. Okay, which is the DC component of that. So that's what's going to be at the input. So if I had to draw this in the next slide, this is what we're doing. So graphically what we're doing is we're applying a voltage here that has a amplitude of 0.14 volts right here. And then we're adding to that 1 volt, which is this 1 volt. So the total signal going in is this. Is the squiggly line around that 1 volt. That's what we're putting in. And we want to know what's the output here at the collector of Q1 and what's the output here at the final output voltage V naught. Okay? And so the question is, how do you go about doing that? Well, we do that by breaking the problem down. But instead of doing that, let's pass back your exams. Okay, so let's first, let me first, Kieran's got your exams, so maybe you can come up with the exams and we can start passing them out. I guess, you know, we're just going to individually call out names because not all of you are here. Normally I would call every name, but we're just going to individually call. He's going to find your exams and then give them to you, I suppose.
You're gonna hand them out?
Yeah, let's find. Well, let me first go through this. Let me first give them the solutions here, because I'm sure they want to see these.
I can pass those around.
Okay, yeah. Just let them pass them around. I guess that's enough for everyone who's here. I'll bring these on Monday too. So, you're going to see the solutions, but I'll put them up on the screen here too. Let me grab that thing that I had. Okay, so these are the solutions to the midterm right here. And so, of course, you remember all the problems. So the first problem, I think, was very similar to things you did in homework, we did in lecture, that sort of thing. This is a problem where the first thing you're doing is just analyzing an ideal op-amp problem, except it's got a capacitor in there. And I think most people did very well on this problem. Then we move on to some of the concepts that are more advanced in this class. Some of you didn't get this in this final form here. And if you didn't, you lost some points because of that. Okay, but then the next stage was trying to plot the Bode plot for that thing when the op-amp is not ideal. And for this, what you really needed to do was just first plot the Bode plot for an ideal op-amp, which would have been this going across and this going all the way up, and then plotting the op-amp Bode plot and having them intersect and seeing that where they intersect, the actual transfer function will just follow the op-amp's transfer function. And I think a good number of people got that as well. Then we run into the slew rate part of the problem. And in the slew rate part of the problem, you had to get the gain at this frequency right here, multiply that input by that gain, and then take the derivative and get that maximum velocity there, maximum volts per microsecond there, and make sure that that was either greater or smaller than the slew rate. It was greater than the slew rate. And then after that, you had to plot that. Okay, and here's the plot for that. So you would first plot the sinusoid dotted line, and then the actual thing would look something like a triangle wave, almost a triangle wave, but not quite. Okay, and then finally part D, probably the easiest problem of the whole thing. Maybe it should have started out with that one there. But this is where you just put the current into the minus and plus terminals of this thing, and that current would not go through this at all because, well, let me go this. It will not go this way at all because that's virtual ground, so you got no voltage across R1. All that current goes out here, and you end up with this final voltage just being the current times that resistor R2. Okay, so that was the first problem. I think people did relatively well on the first problem. It was the second problem that I guess people must not have liked too much. Right? This was more of the physics problem here. This first part was basically putting negative charges and positive charges, static and a mobile charge on this thing. I think people did, you know, okay on that. People were losing points for various reasons there. But it's this last part B that almost no one got, I suppose. That was supposed to be the hard problem, and almost no one got that. What this really is actually a transistor type thing. But it's a transistor that's very different from an MOS transistor. So what it is these junctions out here are P plus junctions, like you're seeing even in the cross section right here. And so when I put a terminal here and I put a terminal here, I can send current through the P-type region. But I can actually control how much current can go through by changing the voltage up here and there, because that will make the depletion regions get bigger. And I actually can make the depletion regions get so big that they cut off this channel, and so the thing doesn't conduct. So I can turn off this thing by putting a large enough voltage on these terminals here because you're creating that depletion region. Yes?
So the question is for the resistance between, this is what confused me, between terminals 1 and 2.
Yeah.
Like, that looks more like the resistance between 3 and 4, like if the current was, because I thought like if I was trying to travel horizontally, I was like, well, I mean, there's no, it's P-type in the second row, it's all N-type in the first row, and it's all N-type in the third row. Like there's no P-in when going left to right. So.
Well, this is P, that's P, that's P. So that's a, you know, that's a short pretty much all the way through that.
Right, but like, I mean, the resistance is between like different, like N and P, right? You have to have N and P to create the resistance.
No. If you just had P, if you just had a slab of material that's P, that has a resistance from this end to that end, right?
But then, like, why do you use
the ends?
Yeah, like.
Yeah, I'm using the ends in order to reduce the amount of P that I see. Because remember what happens here. So if I look at this right here, this P is conductive. That's got holes in it.
Right.
It allows current to flow through. But this minus and that minus is not conductive. And so the fact that I have the N plus allows me to create these static charge regions. And if I were to increase the voltage on these N plus regions, that makes the static charge even bigger, right? It makes the depletion region bigger to the point where the amount of P that I have here gets smaller. And so I'm actually controlling the thickness of the slab of P, which then changes the resistance of that, right? Because the resistance is equal to, it's proportional to the length divided by the thickness T and the width. And so the length and the width stay the same at all times, but my T gets smaller when I increase the voltage on the N pluses. See what I'm saying? Does that make sense?
Oh, okay.
Do you? Or are you just saying that?
I mean,
okay.
Yeah, now that I look, because.
Okay, yeah. It was tricky, actually, and it was, when I think about it, it was a little unfair for you in the end because there were more parts to this problem. So the fact that we had to go from a 2-hour exam to a 1-hour exam, I took out a part that probably would have triggered in your mind that that's what's going on. The first part before this was, tell me the thickness of this depletion region, right? And if you were thinking that way, maybe you would have thought, oh, okay, it's the current going through this P. Maybe not, right? But this had more parts to it, so it was actually easier for the longer exam than for the shorter exam. So you got nailed a bit by the fact that the exam had to be made shorter. Because I think there were parts that would have given you some hints on this. There was also a whole nother problem, so there were actually 3 problems on this. I took that other problem out, which I think was a little easier than this one. I kept the hard problem. But because it was the only physics problem on this. Yeah.
Perception between P plus and P, I think there is a small depletion region.
Yeah. Well, there's not a depletion region. There's just a small hump in the energy diagram. Right? So you could call it a small hump there, but that small hump is not going to prevent current from flowing. Right? Anytime I have P plus with P, the currents will still flow across that. Yeah, so those who've taken 130 or are taking it right now, that confused some people, I think. Because they thought that if I have a junction that's P plus and P, then there's got to be, I need some voltage across that to make it work. No, you don't. Right? That's the way you actually make contact to P, right? In an NMOS device or any device, you put a P plus there so that it contacts the metal very well. But I didn't expect everyone to understand that. It was a difficult problem, right? I told you, every exam I'll put a problem on it that is nearly impossible. One person almost got it, I suppose. So it wasn't completely impossible, but it was a difficult problem. That was a difficult problem on the exam there. Okay, so let's give the exams back now. I could say that the mean on the exam, yeah, let me show that.
Just hand them back?
Yeah, let's hand them back. And so I can hand part of them back too, if you want. Well, no, let me show the mean right here. Go ahead and start handing them back here. Okay, these are the statistics here. So the maximum that you could get was an 86 total. And that last problem was worth 20. Okay, so you might subtract 20 from 86, and that may be the real total that you get. The top score was a 73, which is pretty good actually on this. The average was a 39, and if you did compute that off the 86, that's a 45%. It's a little low for a mean, but if you subtract out that last problem there, you just do problem 1, that's a 57%, which is pretty good, I think. That mean is not that bad on that. So you did well on the parts that you're supposed to do well on. It ended up having too much impossible problem on it because it was a shorter exam in the end. Okay? And so what does this mean here? If you're at the mean, and so what I'm going to do is I'm going to compute your z-scores, and I'm going to show that on Monday. So in other words, we're still putting in all your lab grades and all your homework grades and this grade here. We'll put all of it together. And if you're at the mean, what is that grade going to be in the class? It's probably going to be around a B+. It might be even higher than that, okay, in the class. And so if you're below the mean, then it's going to be somewhere, you know, depends on how far below that mean. But, you know, you'll see that when we actually calculate the z-scores. Remember, z's are something where it puts the mean at 0. If your standard deviation above, you're at 1. If you're one standard deviation below, you're at -1. And you'll be able to see much more clearly on Monday where you stand, right? But if you're at the mean on this, then you probably have something close to a B plus or something like that, okay? Any questions about this? All right, well, let your friends know that you already have your exams back, because they won't. But that's it for today. I think we're over time. Yeah, we're about 6 minutes over time. Depends. What do you want to hold? I mean, if I hold on.